Hello and welcome to this tutorial on machine learning by EDU Onyx. In this project we are going to be performing credit card fraud detection by using several different anomaly detection methods. So I'm really excited to dive in because this is such an incredible application of anomaly detection or outlier detection and is an interesting part of unsupervised machine learning. So let's go ahead and dive right in. For this project, we're going to be using a data set that is hosted on Kaggle.com. So this is the credit card fraud detection data set. It's got an open source database license, so it's free to us to use. Unfortunately, it's behind a... You gotta get an account on Kaggle to go ahead and download this. I'm hoping that we can host it on the EDU Onyx website and you can get it along with the project. However, it's just a simple sign up and provide an email and then you'll be able to access this. So I've already gone ahead and did that and I downloaded this file. It's just a simple CSV file. So you see it's here in my tutorial folder so that I will be able to access that there. So go ahead and pause the video, and whether it's from the EDU Onyx website or from this Kaggle website right here, create an account and download that CSV file. It's going to come as a zip, and extract it and place it in whichever folder that you are going to be completing this project in. Okay, so once that's completed, we can go ahead and just like the previous projects, we are going to be using Conda to launch Jupyter Notebooks and programming our project in Python through Jupyter Notebooks, because that is a great way to make it transferable and work cross-platform. So I'm using Windows, so if you are on a Windows machine, you'll be able to follow along exactly. However, if you are on Linux or a Mac OS, you may have to change a few things to launch your Jupyter Notebook appropriately. But for Windows, go ahead and just type Jupyter Notebook and that will open up the notebook in your web browser. As per usual, we are going to be using NumPy, Pandas, Matplotlib, and sklearn. So if you don't have those packages already installed, go ahead and do conda install whatever the package name is. However, if you have been following along with the projects that we have been completing so far, then you will likely have all of these installed already. But we'll go ahead and do an import check to make sure that we're all running the same versions of these different. And here I was in the wrong folder, so I'm going to go into my tutorial folder. Remember, wherever you type this Jupyter Notebook opens up the folder that you are in currently in your terminal. Okay, so now that I'm here in my tutorial folder, I'm going to go ahead and open up a new Python notebook or Jupyter Notebook, and we can name this something appropriate. Credit card fraud detection, because that is what we are going to be doing today. Okay, so let's start and we'll do generic imports of all of the libraries that we need, and we'll also print off the versions so that we know we are using the same ones. As always, we'll do an import sys to get our Python version. We're going to be using NumPy, Pandas again, import Matplotlib, import, and we're going to need Seaborn once more to do a correlation matrix. We'll also need SciPy. Okay, so let's go ahead and print those off. And we'll do a nice little format here. Format is a great way to substitute variables into strings in Python. So whenever I have to substitute a variable into a string, I usually always go with this .format method. And you can do multiple variables. It all just depends what you need. I'm going to Control-C and copy this a couple of times to speed up this process here. So we have NumPy. Let's make this one Pandas, and we'll switch this here. We are going to need, oh, and I accidentally clicked enter, Matplotlib, We'll get this sorted out. Seaborn. And then the last one, SciPy. I was actually going to wait to import the sklearn until we were doing the machine learning steps, but let's go ahead and do that now actually. Okay, oh, and I'm going to have an error here. There we go. So here are the packages that I am using, Python 2.7 as always, and then these packages and versions here. So make sure you have up-to-date versions of these packages and everything should run appropriately. Alright, but now let's move on because we don't need the overall packages. We need some more specific packages. So we'll dive into that. What I mean by this is we're going to use NumPy and shorten things down. We'll use it as MP. Similarly, we'll do PD for pandas. We need PyPlot for our graphical interface, and we'll use it as PLT, and then we'll import Seaborn as SNS. So go ahead and click Shift Enter here, and those are all good. And so if you have hit an error in one of these steps, and you probably don't have one of these packages installed or modules installed, you can go back to your terminal or open up a new terminal since the Jupyter Notebook is running in this one, and type conda install and then whatever package you are missing. And as long as conda is in your path variables, that will download and install the appropriate module that you need, and then you should be able to come back here and successfully import it. But as long as that's all going and up and running, we are ready to move on. So let's load the data set. We're going to use pandas for this. So if you were successful and you got the data set downloaded and it is in your same folder as your Jupyter Notebook file is now, then all it's going to take to get this into our notebook is a read CSV function. creditcard.csv, and that's going to pull this in as a pandas data frame. So let's go ahead and click Shift Enter and make sure this works. And we're thinking, because this is a pretty big CSV file, but we were successful. As soon as this number pops up, you know you're good to go, and it looks like it has it. So let's start exploring the data set a little bit so we know what we're working with. The first thing I like to do is a data.columns so we know what is included in the data set. Okay, so it looks like we have about 31 different columns going from time all the way to amount and class. So here we have V1 through V28, and these are actually the result of a PCA dimensionality reduction that was used in order to protect sensitive information in this data set. For example, we don't want to expose the identity of the individual who made the credit card transaction. We also don't want to expose stuff like location, but this is a time in a separation from previous transactions and amounts. And then our class here is going to be a 0 for it's a valid normal credit card transaction, and then 1 is going to mean a fraudulent transaction. But let's go ahead and learn a little bit more about that. So let's do a print data.shape so we know what's here. Okay, so we have 284,000 credit card transactions with 31 columns, all of this information for each transaction. Let's do a print data.describe. And we need, lost our print function here. Get the correct parentheses. And this will give us useful information about each column. So this gives us the mean, min, max, etc., and count for each column. So you see here the count is the same for each of these parameters, so that means that we're not missing any data, so that's helpful. This is formatted weird. It's not showing us the middle V's. That's what these ... dots mean here. The class, though, is the important part. So we have 284,000 of these. We have a max of 1, that's the fraud. And we have a min of 0, that's the standard. If you see this mean, this looks like it's really close to 0. So that must mean we have way more valid transactions than we do fraudulent transactions. So we're going to have to account for that as we go on. One thing I'm also going to do, since this is such a large data set, in order to save on time and computational requirements, I am going to sample only a fraction of this data set. So instead of using all 280,000, I'm going to do data equals data.sample. Fraction equals 0.1, so I'm only going to take 10% of the data. And just so that we have the same data, we're going to define a random state here. And then I'm going to do print data.shape just to make sure that worked. Okay, so now instead of 284,000, we have 28,481. Still have all of our columns, but this is a much more reasonably sized data set to work with. Now, if we used all 284,000 of these, we'd probably get better results. However, for the sake of computational requirements, I'm going to go ahead and cut this down right now so that we have more manageable data to work with. So let's keep exploring our data set. We've imported our CSV file. We've looked at each of the columns and the column names and the distributions. Another way to do that visually is going to be a plot, a histogram of each parameter. So to do that, it's really easy with the pandas data frame. We're going to do data.hist, and I'm going to define a figure size here to make it a little more pretty. And then we need a plt.show, since this is going to be a pie plot. Works hand in hand with matplotlib and pandas. And if you go ahead and click Shift Enter there, we should be able to pull this up after it gets done thinking. Okay, here we go. So here is all of the histograms. And so this looks like most of our V's are clustered right around 0 with some fairly large outliers or maybe no outliers in regards to this one. The interesting thing here is, again, we see that we have very few 1 values or fraudulent transactions in comparison to our valid transactions. So that's kind of surprising, although it makes sense since this is real world data. But let's go ahead and actually calculate the number of fraudulent cases that we have and the number of valid cases that we have, so we can get an outlier fraction that is going to go into our future methods, our anomaly detection methods. So to do that, we're going to just start with a comment here. So fraud is going to be equal to data, and we can index this by saying just data and class end bracket where class is equal to 1. So that is our fraudulent case, and we'll have a valid is going to be equal to the data, and we can index this with the class again. However, this time we want equals to 0. These are going to be the valid transactions. Okay, and we're using this to calculate a percentage of fraudulent cases to valid cases. So we can do an outlier fraction is going to be equal to the length of fraud divided by, now we got to be careful here. If we don't use a float here, it's going to round us to an integer, which would round us to 0 since this is going to be really low. So what we need to do to carry our decimal points is type float to turn this into a float, which is the type of data, and then our length valid. So this is going to be the number of fraudulent cases divided by the number of valid cases with decimal points. So let's print this out. And I'm also going to print out the number of fraud cases. And we'll make this nice. We'll use another format because it's always good practice. And we'll just do length fraud here. Okay, and we'll also do a print valid cases dot format length valid. Okay, so we'll go ahead and click Shift Enter here. So we actually see that we only have about 0.17% of our database is fraudulent cases. And that's a total of 49 fraudulent cases and 28,000 valid cases. So we have a huge disparity here between the fraudulent cases and the valid transactions. So this is going to be harder to predict, but it makes it it's important to carry all this information through, because if you have an overrepresentation of fraudulent cases in the data set that you're using to train your algorithms, you're going to end up predicting more fraud than there actually is. So it's important that we consider this underlying percentage of fraudulent cases, this outlier fraction, before going into actually building our networks. One more thing that we should do is build a correlation matrix to see if there's any strong correlations between different variables in our data set. This is going to tell us whether or not we need to remove things like in previous projects it was the ID of our data sets. We don't have an ID here. It's also going to tell us if there are strong linear relationships, which we could then use different linear methods to predict these. It's also going to show us which features are important for the overall classification. So here is our correlation matrix, and the pandas data frame, which is the type our data set is in right now, makes this really easy with the dot correlation function here. And then we just simply do a pie plot figure. So we'll have plt.figure and fig size to make this nicer again. And we're also going to use the Seaborn here. So this is when we're going to do the SNS heat map. And this is going to turn our correlation matrix into a very nice visual display that is easy to read. And plt.show once again, and Shift Enter to pull this up. And here we go. So here's our correlation matrix with the heat map. So if you see, we have a lot of values right here really close to 0. So there isn't strong relationships between our different V parameters, the V1 through V28. Most of them are fairly unrelated to the others. However, what we do care about is the class. So we see there's some variations in the relationships between the different parameters and our class here. So the lighter ones are going to be a positive correlation, whereas negative would be a strong negative correlation. So we see maybe V17 and V11 stronger positive, whereas V17 would be a stronger negative correlation. There isn't a strong correlation between amount and whether or not it was fraudulent, or time and whether or not it was fraudulent. That could be some interesting information to take away. We don't see many one-to-one correlations here in our correlation matrix, so that's good. We don't need to pull out any of our columns before we dive into doing our actual machine learning. But before we actually get started with that, we need to format our data set slightly. So let's go ahead and do that. So we need to get all of our columns from the data frame. To do that, we're going to do columns equals data.columns.toAlist. So that'll generate a list of the columns. And then we want to filter the columns to remove data we do not want. So in this case, there's only going to be one that we're pulling out. And that is going to be our class. It would be very easy to predict which ones were fraudulent if we told our network which ones are fraudulent. So this is unsupervised learning since it's anomaly detection, so we don't want the labels to be fed to our networks ahead of time. So we want to store the variable we're predicting on as well, and that's going to be the target here. And the target, once again, is going to be class. That's what we were trying to predict. So we can have our X data, and what we're going to do is the data, and this is going to be the columns, which we pulled the class out of, and we can have Y is equal to data, and this is going to be the target. So only the class. So let's go ahead and print the shapes so that we know what we are working with, and if everything worked correctly, we'll be able to see that here. Okay, go ahead and click Shift Enter here. So indeed it did work. We now have 30 columns in our X, which was everything except our class label, and then our Y is a one-dimensional array that has the class labels for all 28,000 samples from our data set. So that's exactly what we wanted, and everything is set up now to go ahead and start building our networks. We're going to use an isolation forest algorithm as well as a local outlier factor algorithm to try to do anomaly detection on this data set. However, that is going to be in the next video. I'm going to stop this one here since we have successfully imported, pre-processed, and explored our data set. We have put ourselves in a position to pick correct machine learning algorithms and methods and produce results that are going to be meaningful and accurate. So keep following on in the second video, and I hope everything went well up until this point. Thank you very much.